Hi everybody. Okay, welcome back. So I'm going to be up to number 3. This is the third of my presentations on intermediate level of the periodic table of elements. And the periodic table of elements, like I said before, is the world's greatest cheat sheet. I love this place. Okay, so we're talking about atoms. So in our first video, just a quick review. In our first video, we spoke about the elements and their positions, meaning that their positions show us the properties. In our second video, we talked about how every atom is electrically neutral, which means that they have the same amount of protons as electrons. We also spoke about the atomic number. The atomic number of the let's bring it up here. The atomic number tells us how many protons there are, and because it's electrically neutral, it tells us exactly how many electrons there are. In this chart, we also have the element symbol, and again, that's two-letter abbreviation, a one or two-letter abbreviation. Sometimes it's three. If you look all the way down here, UUO and UUS and UUP, they haven't figured out some of them yet. But that's the element symbol, and again, B makes boron, but then how does well, let's pick a funny one. AG makes silver. It's a Latin name. And then we have the atomic mass. That is the mass, not the weight. Although we use the weight because weight and mass here on Earth are the same thing, but it's the mass. It's the weight of one element of gold. On this chart, we have in this little box here on the side. This is my favorite chart, by the way. ScienceNotes.org and Helmsley. Check it out. So on this chart here, you have the number of electrons in the shells. So you'll notice that the first shell has 2 electrons, the second shell has 8, and the third shell has 18. So these are called orbitals or shells or energy levels. All the names mean exactly the same. So, but there's something else. There's something called a neutron. Now again, back to this picture. This is the first picture of an atom, and inside is the nucleus, right here. That's the nucleus. Then we have the electrons flying around in orbit and the shell in an energy level. And those electrons flying around in the have a very small amount of weight, almost weightless. It's like one. If a proton weighs one, an electron is 1/2000 of a proton. That's how little it is, and how weightless, or not weightless, but it has to have some weight. So what we're going to go back to this picture over here, but you know that there's one more thing inside of the atom called a neutron. Now, first of all, let's go back to gold here for a second. Now, you see that this picture here has a slightly different configuration. It doesn't have the electron valence shells on the side, and it doesn't tell us how many electrons there are. And like I said, every one of these charts could have a slight variation, but the truth is these charts are used all over the world exactly the same way, and they look exactly the same. So in other words, in China or in Russia, they use the same chart that we're looking at. That, again, Mendeleev, this guy, Dmitry Mendeleev, created this chart in 1860. You have to understand how unbelievable. 1860, he had no Google, he had no Siri, he had none of these, barely an abacus. I don't even know if an abacus would have helped him. But he figured out about 60 different elements. And then he also left spaces because he knew that if there was a 79, then there had to be an 80, and there had to be a 78. And even if he didn't have the 78, he already knew that something was similar. So in other words, 78 was similar to 79 in many respects. That's why teaching about the properties of elements is very important. Okay, so in this chart we have the 79, AU, gold. Again, that's that Latin word. I have no idea. And then it has this mass of 196. Well, again, we said that 79 was the number of protons, and 79 is the number of electrons. But the electrons weigh nothing, right? So what's the 196? So that's the neutrons. So there's a trick to this to find out how many neutrons there are inside an atom. So what you do is take a trusty calculator, because I'm not going to bother and by accident make a mistake on my calculations here. especially not on public video. So we take 196, let's round it off to 197. 197, and we're going to minus the 79. 79, that equals 118. So that tells us that we have 118 neutrons. So here's another piece of information that we can get from this chart, or the PTE, again, the world's greatest cheat sheet, that we have 100, what did I say, 119, 170 neutrons. That's how many neutrons there are. Let me keep this up. 196, 118. So you have 118 neutrons. 100, I'm going to write this down because I don't want to forget it. 118. So 118 neutrons. And you can do this for everyone. Some of them are easy, and some of them are hard. For instance, carbon. Carbon has an atomic number of 6. That's the number of electrons and number of protons. And then we have C. That's the simple name. See, this chart is totally different. And then it has atomic mass of 12, what they call atomic mass units. So that's 1201. So it takes 12 minus 6, and you have 6. So in this case, it's real simple. We know that carbon has 6 protons, 6 electrons, and at the same time, it has 6 neutrons. Because they found, by the way, that a neutron and a proton are about the same weight, mass, about the same. But there's something more about this. Let's go a little bit further. Let's look at the first column of the PTE. First column is called the reactive metals, okay? And what these do, they are very reactive. You take lithium or sodium and you put them into water and they will actually start to fizz and pop and bubble. And I've done this in class and actually had little sparks fly out. It's a lot of fun. Potassium also, rubidium, cesium, and francium. They all have the same property that they have one electron in their outermost shell. Hydrogen has 1 electron. That's it. But hydrogen is a gas. We're going to separate him a little bit. That's why it's in red. But lithium, sodium, potassium, etc., they all have one electron in their outermost shell. I call these atoms unhappy atoms because they have that like one little hanging out on the side over there, right? Lithium is 3 on the periodic table. So if we look at the periodic table, let's go quickly back up here. So if you look at the periodic table, lithium is number 3. So 3 protons, 3 electrons. So on the first shell, if you can see in the little numbers on the side, the first shell has 2, and that's complete. Because the first shell can hold 2, and that's it. The second shell can hold up to 8. But in lithium's case, it only has 1. So it's a sad electron. So I call it a sad electron because it has this one little electron that it kind of hangs on over there. It's important, but it kind of hangs on the outside. Sodium, on the other hand, has 2 in its first shell, 8 in its second shell, that's 10. And then the third shell also has a 1. It also has that one little electron. That makes 11, right? 2 plus 8 plus 1 makes 11. And you can see that number over here. Now, even without cheating, that you have these valence electrons here, you don't need this chart, but I like this chart because it makes it easier to understand. You can see that that 1 is just hanging out on the side. It hangs out by sodium, it hangs out by potassium, hangs out by rubidium, and there's only one in each one of them. 1 electron in its outer shell. Let's go to this column, and they're called groups, by the way. Group or a column or a family, because families share traits, right? Families share traits. So all of the Li, Na, K, they all are one family. They all share the trait of having that 1 electron on the outside, and they're very reactive. If you go to this group here, okay, I'll call this group 7. So that's fluorine, chlorine, bromine. And if you look up here, okay, it's in column number 17. I'll call it column 7 for now for a reason. You look at each one, if you look at the valence shell, each one has a 7, 7, 7, 7, 7, 7. In other words, their last shell has 7. So a complete shell is 8. Even when there's 18, a complete shell is 8, and they're happy when there's 8. That's why these are called the noble atoms. The noble atoms all have 8. For helium, it has complete first shell, 2. Neon has a complete second shell, that's 8. Argon, etc., etc., etc. So what they have is a complete outer shell, and they're happy atoms, noble atoms. Not only are they happy, they are noble. They don't mix with anybody. But mixing is the special word I'm trying to get to here. If you look at column 1, it has 1 electron in its outer shell. If you look at column 7, they have 7 electrons in their outer shell, meaning that you can get rid of 1 electron a lot quicker than you can 7. So they're unhappy too because they don't have a full shell. So in other words, everybody on this chart is pretty much unhappy except for the nobles. The nobles don't have to mix with anybody because they have a complete shell. But from 1 to 7, they're all unhappy. However, the guys in the 7 have a kind of an advantage. They can't get rid of 7. You can get rid of 1, however. And that's why let's look at Na and let's look at Cl. You might already know where I'm going with this. Because NaCl gives us a very, very common mineral that we need all the time. And Na plus Cl gives us sodium chloride, which is table salt, which we need to live, which we use on our pizza. We need sodium chloride. So just by looking at this chart and knowing that group number 1, family number 1 has 1 electron, and family number 7 has 7 electrons, and we know that the 2 of them can get together. You can already guess which atoms, which elements will be able to match up with the others. For instance, we know that Na and Cl match up. So if Na plus Cl can match up, and pretty much anybody in 1 can match up with 7. 2 matches up with 6. 4 matches up with 4, plus 4 plus 4 is 8. It's called the octet rule. You can look it up. The octet rule, O-C-T-E-T, tells us that a happy atom has 8 on the outside, and that you can add 1 to 7, 2 to 6 to make 8. Okay, I'm going to stop here. Look up Mendeleev. We have Mendeleev told us about the periodic table. He built it. It looks totally different than what it looks like now. But even he left parts. We have the families, the groups going down to columns. So each column is a group. Each column is a family. Families share traits. And we know that 1 will go with 7. 8 doesn't go with anybody else. Okay, we're going to stop here, and we'll have more about this great chart, this wonderful chart, the greatest cheat sheet in the world. Take care.